In this lecture, we're going to go over another example of how to calculate the magnetic potential. In this case, it's for an infinitely long solenoid. So in the textbook, this is example 512. So let's say you have this infinitely long solenoid. So it's a cylinder with a wire coil wrapped around it, and we want to find out what is the magnetic potential A in this. So we already worked out previously that the magnetic field is mu zero, the number of loops per unit length, times the current going through in the direction. In this case, it would be the z direction, which is along the axis, the central axis of the solenoid. But now we want to find out what's the potential from there. So it turns out that since we've chosen to study an infinitely long solenoid, then we can't use Coulomb's law, where we said that the magnetic potential was mu zero over 4 pi, the integral of the current density over the distance dotted into the area. So anyway, we can't use that one because the assumption we made in there was that the divergence of A was going to basically go to 0 at basically R goes to infinity. So we can't use that. So instead we're going to try something else. So what we're going to look at is something basically called the flux. So if we take the integral of the magnetic potential over a path, then from, I believe it's Stokes' theorem, we could look at the integral of the curl of the potential dotted into the area. And so in this case, the curl of the potential is the magnetic field. So we have the magnetic field dotted into the area, which we're going to define as the magnetic flux. Okay. So basically, we have this loop where we're integrating over, and that becomes the perimeter of an area. And so we're looking at the magnetic field that is now going through this area. Okay, so the flux is the amount of magnetic field going through that area. So for a solenoid, this is pretty simple. The area is the ends of the cylinder that comprises the solenoid. So what we're looking at is the flux of the magnetic field as it goes through this area, this circle at the end of the solenoid, at the end of the tube. Okay, so let's calculate that. So the flux of the magnetic field through the area is mu zero Ni dot the area, which is also in the direction of Z. So again, I'll draw the picture of this solenoid. So this area here has a direction in the Z direction. Okay, the magnetic field also happens to be pointing in the Z direction. So they're basically parallel to each other. And since it's a uniform magnetic field, I can take it out in front of the integral, And what I'm left with is basically the area. And so our flux is mu 0 Ni, the area, which is pi s squared. So s is going to be the radius of the end of the solenoid. Okay, so that's our flux. So therefore, the integral of the magnetic potential integrated over the path or the circumference of the end of the solenoid is going to be equal to our flux, which is mu 0 Ni pi s squared. Okay, so now if the magnetic potential is also uniform inside the solenoid, then we can rewrite this as A, the integral dl like so. And the integral of the path is just the circumference. So inside the solenoid then, what we have is the magnetic potential is mu 0 Ni pi s squared divided by 2 pi s. So I cancel the s's, I cancel the pi's, and I get A is equal to mu 0 Ni s over 2. And that is now in the direction of phi. So if I put the vector notation on it, I have a magnetic potential, which is now acting in the phi direction. And this is for s less than the total radius of the solenoid. So basically that's for the inside the solenoid. If you look at what's going on the outside, then what we have is the flux is mu 0 N, the current I, times the area, which is pi r squared. So we're just, basically the largest the area can be is pi r squared, where capital R is the radius of the solenoid. Okay, so that means that A times the circumference, 2 pi s, so that's the circumference of the loop, is equal to mu 0 Ni pi r squared. So A becomes mu 0 Ni pi r squared over 2 pi s. So the pi's cancel, and that's about it. So what we're doing is we're left with the magnetic potential is mu 0 Ni r squared over 2s in the phi direction. So that's for s, which is greater than or equal to the radius r. So basically I should have drawn the picture first before I did that. But if this is our solenoid, right here. So on the outside case, what we have is a radius, capital R, and we're now drawing a loop with a radius S. That's on the outside of the solenoid. So now we have so the magnetic field is uniform inside the solenoid and 0 on the outside of the solenoid, and the magnetic potential has a certain value inside and another value on the outside. Very analogous to something like the electric potential around a capacitor. Okay, so what I basically can leave up to the students is that what you can check is that if you take the divergence of this magnetic potential, then what you would have is the divergence of mu 0 ni over ni over 2 times s in the phi direction. So this is for the case on the inside the solenoid. And when you take that divergence, you get 1 over s sine theta mu 0 ni over 2 ds d phi, because you only have a component in the phi direction, and that is equal to 0. So that's for when the radius is less than the total radius of the solenoid. On the outside, what do we have? Well, we have the divergence of A, which is the divergence of this formula, mu 0 ni capital R squared over 2s in the phi direction. And that's equal to 1 over s sine theta mu 0 ni r squared over 2 d phi of 1 over s, which again would give you a 0. So the good news is that even though we didn't use that statement that the divergence of the magnetic potential is 0, but what happens is the result we get satisfies that criteria. We can also check the curl. So the curl of A is equal to the curl of our equation inside, mu 0 ni s over 2 in the phi direction. Now remember, there's no radial component, there's no theta component, there's only a component in the phi direction. And so when I apply this, I get 1 over s sine theta times the derivative with respect to theta of sine theta mu 0 ni s over 2 in the s direction plus 1 over s minus the derivative with respect to s mu 0 ni s over 2 in the theta direction, which is then equal to mu 0 ni over 2 cosine theta sine theta in the s direction minus mu 0 ni 2s over 2s in the theta direction, which leads me to mu 0 ni times 1/2 the cotangent of theta in the s direction minus the theta direction. So essentially what we get is that magnetic field that's operating in the z direction.